Welcome to the Deep Dive, your express route to becoming truly well-informed. Today, we're kicking off something special, our CSWIP 3.1 Welding Inspector Exam Prep Series. Now, for anyone diving into this, CSWIP is the certification scheme for welding inspection personnel, and 3.1, that's the senior welding inspector level. Our aim here isn't just, ticking boxes on multiple choice questions. We want to give you that deep understanding of why the answers are correct. Real knowledge you can use way beyond the exam. Think of this as your shortcut to really nailing those core concepts.
Absolutely. Understanding these fundamentals, well, it's non-negotiable, really. When you genuinely grasp these ideas, it builds huge confidence for the exam, sure. But just as importantly, it translates directly into better practical work, sharper decisions out there on the job. We're here to help connect those dots for you, turn memorization into actual understanding.
Okay, let's dive right in then. We'll pose a question, run through the options, and then really break down the right answer. Get ready to think along with us. First question coming up, here it is.
Assuming that the welding process, material thickness, carbon equivalent, and the welding parameters are all the same, which of the following joint types would normally require the highest preheat temperature? Your options are A, edge joint, B, lap joint, C, single V, or D, T joint. Take a second. Picture the heat flow in those joints. What do you think? All right, ready? The correct answer is D. T-joint.
And this is where understanding heat transfer in welding really becomes critical. A T-joint, just by its shape, it presents a unique challenge for managing heat. You're joining basically three planes of material together in that T shape. That creates a much bigger thermal mass and significantly more surface area compared to the others.
Okay, more mass, more surface area.
Exactly. So it acts like a really efficient heat sink. It just pulls heat away from the weld zone much, much faster.
Okay. This fast heat dissipation means quicker cooling. In the weld metal, and the heat-affected zone, the HAZ.
Right, faster cooling.
And rapid cooling.
Yeah.
Well, that's where problems can start. To counteract that, to slow things down and avoid issues like hydrogen cracking or lamellar tearing or getting brittle microstructures, you need higher preheat. It's all about controlling that cooling rate, giving the metal the time it needs to, transform properly.
That really makes sense. The geometry itself dictates how the heat behaves. So with this T-joint challenge, are there specific codes or standards that kind of flag T-joints for special preheat attention, or maybe different inspection methods because of this? And you mentioned cracking, but what other defects are we trying to dodge with preheat on T-joints?
Yeah, good points. Many codes, like ASME or API, they often have rules. Maybe not saying T-joints specifically every time, but they talk about increased restraint or thermal mass, joint type. And when you put those factors together for a T-joint, it points towards needing higher preheat. Besides cracking, you're also fighting against excessive residual stress. T-joints are inherently quite rigid.
Right.
So they resist contraction more as they cool, which builds up stress. That can lead to distortion or even lamellar tearing, especially in the through thickness direction of the plate, forming the stem of the T. So preheat isn't just about stopping immediate cracks. It's about long-term integrity, dimensional stability too.
Makes perfect sense. Okay, so from joint geometry influencing heat, let's switch gears to material composition. Stainless steels next. Question 2. In the welding of austenitic stainless steels, the electrode and plate materials are often specified to be low carbon content. The reason for this is, your options, A, to prevent the formation of cracks in the HAZ, B, to prevent the formation of chromium carbides, C, to prevent cracking in the weld, or D, minimize distortion. What's the critical reason behind specifying low carbon here? The correct answer is B, to prevent the formation of chromium carbides.
Yes, and this is a really, really important concept in stainless steel metallurgy. It's all about corrosion resistance. You see, with austenitic stainless steels, if they have higher carbon content and they get heated during welding into a specific temperature range, roughly 450 to 850 Celsius.
The sensitization range.
Exactly, the sensitization range. The carbon atoms can move around, they migrate to the grain boundaries, and there they combine with chromium to form chromium carbides.
Okay.
Now, this process, sensitization, it depletes the areas right next to the grain boundaries of chromium.
And chromium is the key element for corrosion resistance.
Precisely. It forms a protective passive oxide layer.
Yeah.
If you pull chromium out of those areas at the grain boundaries, they become vulnerable, like little highways for corrosion. This makes the steel highly susceptible to intergranular corrosion in aggressive environments.
Wow.
So using low-carbon materials, the L grades like 304L or 316L drastically reduces the amount of carbon available to form those carbides. It preserves the chromium where it needs to be, maintaining the corrosion resistance.
Okay, let's unpack this a bit. So it's not just about the weld itself, but the material's long-term ability to resist its environment. That's a huge aha moment. These seemingly small choices, like specifying L grade, have massive implications down the line. But what happens if sensitization does occur and isn't caught? Are we talking minor surface rust or something worse? And can an inspector even see sensitization? Or is it hidden?
That's a great question. It really shows why L grades are vital. If sensitization happens and that component goes into a corrosive service, think chemical plants, paper mills, even some food processing, those chromium-depleted grain boundaries corrode preferentially. It's called intergranular corrosion, or IGC. If there's stress involved, it can be intergranular stress corrosion cracking, IGSCC.
Okay, so not minor issues.
Definitely not minor. These can lead to sudden catastrophic failures, pipes, vessels, structures, failing with little warning because the damage is internal along those grain boundaries.
Wow.
And to your other point, no, an inspector can't visually identify sensitization itself. You can't just look and say, that's sensitized. You might eventually see the results: pitting, rust, cracks. But the underlying condition isn't visible. Detecting it usually needs lab tests, like an oxalic acid etch or other electrochemical tests on samples, which is exactly why preventing it through material selection and procedure control is paramount.
That really hits home the importance of prevention. Okay, moving from materials to welding parameters themselves, let's tackle question 3, preheat temperature. The options are: A, may be increased by an increase in travel speed; B, may be increased by a reduction in material thickness; C, may be increased by an increase in electrode diameter; or D, none of the above. Think about how these factors interact with the weld's thermal cycle. The correct answer here is A, may be increased by an increase in travel speed.
Yeah, this one can seem a bit backwards at first glance, can't it? Faster speed, less heat, maybe less preheat.
Right, that's what you might initially think.
But it's about the heat input per unit length of the weld and how that affects the cooling rate. When you increase travel speed, keeping current and voltage the same, you're essentially applying the heat source to any single point for a shorter time.
Okay, less time at each spot.
Which means lower heat input per inch or per millimeter of weld length. And critically, lower heat input generally means faster cooling for the weld and the HAZ.
Ah, faster cooling again. I see the pattern.
Exactly. And fast cooling, as we've discussed, can be bad news. Brittle structures, higher hardness, increased risk of cold cracking, especially in certain steels. So to counteract that faster cooling caused by the higher travel speed, you need to increase the preheat. The preheat acts like a thermal buffer, reducing the temperature difference, slowing down the overall heat loss, and promoting better metallurgical results.
So, okay, what does this mean practically for the welder or the inspector on the floor? If, say, production wants to speed things up, increase travel speed, can they just dial up the preheat and call it good? Or is it more complicated?
Oh, it's almost always more complicated. It's rarely just a simple swap. While increasing preheat can compensate, there are limits. Too much preheat can be uncomfortable and unsafe for the welder.
True.
And metallurgically, excessive preheat can cause other problems, like grain coursing or even burn through on thinner materials. So if travel speed goes up significantly, an inspector has to verify, are these new parameters, including the higher preheat, still within the qualified range of the WPS, the welding procedure specification?
Ah, the WPS.
If they're not, it could mean the WPS needs requalifying, which involves testing, time, money. It really shows how interconnected everything is. Change one thing, you might have to reassess the whole procedure to ensure quality and compliance.
That definitely highlights the need for that holistic view. Okay, shifting from heat management now to verifying material properties through testing. Question 4. In which of the following mechanical tests would show a change in the material from ductile to brittle with the use of a transition curve? Options: A, tensile test. B, Charpy test. C, fusion zone test. Or D, all of the above. This tests your knowledge of material behavior and how we measure it. And the correct answer is B, Charpy test.
Yes, the Charpy impact test. It's specifically designed to measure a material's toughness, its ability to absorb energy before fracturing, and, crucially, its tendency to become brittle at lower temperatures.
How does it work, basically?
You take a standardized notched sample of material and hit it with a swinging pendulum. You measure how much energy the sample absorbs when it breaks. Now, the key part is doing this test over a range of temperatures from very cold up to warmer temps. When you plot that absorbed energy against the test temperature, you get the ductile to brittle transition curve. And that curve clearly shows the temperature, where the material shifts from behaving ductily, absorbing lots of energy, deforming before breaking, to behaving brittly, where it breaks suddenly with little energy absorption.
Right, the transition temperature.
Exactly. And knowing that temperature is absolutely vital for choosing materials that will be safe, especially in cold environments where many steels can become much more brittle. It's fundamental for preventing brittle fracture.
Okay, here's where it gets really interesting and so important for safety, right? Structural integrity. You mentioned safety. Can you give a real-world example where knowing this transition was crucial, maybe prevented a disaster, or led to rejecting a material?
Oh, certainly. The classic example, unfortunately a tragic one, that really drove this home was the failure of many Liberty ships during World War II.
Ah, yes, I've heard about those.
They were mass-produced welded ships. The steel they used was fine in warmer waters, but became incredibly brittle in the cold North Atlantic. Many ships suffered catastrophic fractures, sometimes just sitting at anchor. Investigations found the steel had a high ductile to brittle transition temperature. It became brittle at those cold ocean temps.
Wow, just like that.
Yeah. Today, understanding this is essential for anything operating in the cold Arctic structures, pipelines, bridges. Materials are specified with minimum Sharpie toughness at the lowest expected temperature. It ensures they stay ductile and resist brittle fracture. Without that testing and understanding, we'd be building potential failures into structures.
That's a stark reminder of why this test is so fundamental. Okay, final question for this deep dive, focusing on welding procedures. Question 5. Essential variable. What is it? A. In a WPS may change the properties of the weld. B. In a WPS may influence the visual acceptance. C. In a WPS may require reapproval of a weld procedure. Or D. All of the above. This is core to welding quality control. And the answer is D. All of the above.
Spot on. This gets to the heart of the WPS and quality control. An essential variable. Well, it's any parameter in that WPS that's considered important enough that changing it could significantly alter the weld's properties. We're talking mechanical properties, strength, toughness, hardness.
Okay.
It could also potentially affect visual acceptance, things like the bead shape, or maybe increasing the risk of certain defects.
Right.
And crucially, because changes to these variables are considered so significant, altering one outside its qualified range typically means you have to requalify the entire welding procedure.
So you can't just change it on the fly.
Exactly. You have to prove through testing that the procedure, with that change, still meets all the necessary codes and standards. Think about things like the welding process itself, like switching from SAMO to GMAW, the filler metal type, the preheat range, big changes in thickness. Those are all typically essential variables. They're the guardrails ensuring consistency and preventing changes that could compromise the weld's quality or safety.
That really makes it clear how tightly controlled welding needs to be. Every detail in that WPS matters, and these essential variables are the absolute non-negotiables. What's a common essential variable change you see causing problems or leading to requalifications out in the field? Any common misunderstandings about what's essential versus non-essential?
A very common one is changing the welding position significantly. Say, a WPS qualified only for flat position welding. Trying to use it for overhead welding usually requires requalification. The heat input, pedal control, everything changes.
Makes sense.
Another one is the material thickness range. Welding much thicker or thinner material than the WPS was qualified for is usually an essential variable change. Or changing the base metal type, the P number, or the filler metal type, the F number. Those definitely impact properties. The misconception. Sometimes people think, well, the weld looks okay. But the inspector's job is to verify compliance with the qualified WPS. If an essential variable was changed outside its allowed range, the WPS isn't valid for that weld anymore, even if it looks good visually. It needs requalification to verify its properties and ensure safety. That's where the inspector really adds value.
That's a crucial distinction for anyone getting into inspection. Wow, okay, we've definitely covered a lot today. A real deep dive into some critical concepts. Big congratulations to everyone listening for sticking with us and thinking through these questions. Dissecting the why behind the answers is so valuable, not just for the exam, but for being confident and competent out there. That deeper understanding is what the deep dive is all about.
And if we connect this to the bigger picture, the real mark of an expert inspector isn't just recalling the right answer from a list. It's understanding how all these things are interconnected, how joint type affects heat, how carbon affects corrosion, how speed affects cooling, how the WPS controls it all, understanding why it's right, and seeing the ripple effects. That's the key. That systemic view is incredibly powerful.
Couldn't agree more. So keep reviewing your notes. Look for more examples of these principles in action. Remember, every question is a chance to learn. This deep dive was just a stepping stone. Keep building that knowledge base for welding inspection. We'll catch you on the next deep dive.